In part 6 of the Unit 2 notes, we are going to be covering states of matter and intramolecular versus intermolecular forces. Now you're all familiar with the three primary states of matter, solids, liquids, and gases. You know what they look like on the macro scale, but today we're going to be talking about why they behave the way that they do on the macro scale, and that has to do with what they look like on the molecular scale. Now, for solids are going to vibrate in place, but they do not really move around within their structure. So you can see from the picture on the right side, our solid molecules are very tightly packed. So as they're kind of vibrating in place, there's nowhere else for them to really go. Solids have their own definite shape and volume regardless of container. In a solid, particles are tightly packed. They only expand slightly when heated, and the tight packing of atoms or molecules makes solids incompressible, or at least mostly incompressible. So if I push down on this solid up here, there's really nowhere else for those atoms to go. And of course, you may or may not be familiar with the fact that liquid water is actually more dense than ice. So for the most part, solids are always going to be the most dense form of a piece of matter, but with H2O, it's actually the opposite. Liquid would be more dense and ice would be less dense, which is the reason why ice would float on water. Now, for the molecular motion of liquids, liquids vibrate and can flow within the confines of a container. If you zoom into the molecular scale, it looks somewhat similar, but there's a little more space in between each of these molecules, which means that now these molecules have the ability to flow past one another, which gives liquids their ability to flow on the macro scale as well. So a liquid flows, has constant volume, takes the shape of its container. The particles are not rigidly held in place and are less closely packed. Liquid particles are able to move past one another, which allows liquids to flow and take the shape of their container. Liquids have constant volume, are slightly more compressible than solids, and expand when heated. Now for gases, if we were to zoom in, you can see in our picture here that they're very spaced out. And if we were actually on this scale, these molecules probably wouldn't even be this close together. You would probably only see the one of them within the box. Gases separate and move rapidly without colliding or interacting with each other very often. A gas not only flows to conform to the shape of its container, but also fills the entire container or the entire volume of its container. Compared to solids and liquids, gas molecules are very far apart and are easily compressed. And gases have much lower density compared to liquids and solids. So if we were comparing these three states of matter to each other, solids and liquids aren't that dissimilar. They're fairly close together in molecular structure, whereas gases are completely different because their molecules are really nowhere near each other as they are zipping around within whatever container they happen to be in. Okay, within this picture, we can see the three phases of matter side by side under similar conditions. So in all three instances, we have a sealed Erlenmeyer flask. With our solid, we can see that we have these very organized rows where there's really no space for these molecules to separate and move past each other. The liquid still kind of tightly packed, but the molecules can now move past one another in order to flow. And then with our gas molecules, they are completely spread out throughout the entire container now. And you can see that they have additional speed based on the way that they're drawn here with those little shadows. So gas molecules, the most motion, also the fastest. But very important to note that all phases of matter do have molecular motion. This is a common misconception that students have. They think that it's only the liquids and gases that move. But the solids, they will vibrate in place. That's still considered molecular motion. All right, next up, intramolecular versus intermolecular forces. And these are the forces that cause atoms and molecules to stick together. The prefix of intra versus inter means within, and inter means between. So an intramolecular force is the force inside of the molecule. It's what holds the atoms together. So if I'm talking about, say, a water molecule, this would be the covalent bond that holds the oxygen and the hydrogen together, and then this covalent bond. So those are considered intramolecular forces. But what about the force that holds one water molecule close to the water molecule that happens to be next to it? There's some kind of attractive force there as well, otherwise you wouldn't have solids and liquids. So that is called an intermolecular force because it is the force between the molecules. They consist of dipole-dipole interactions, hydrogen bonding, and London dispersion forces, which are forces that we'll talk about much later on in the year. For right now, the main thing that you need to know is intramolecular forces hold the molecule together, and intermolecular forces helped one molecule to be attracted to the one next to it. Here we can see another example of inter and intramolecular forces. So here we have HCl, which is hydrochloric acid, the hydrogen and chlorine being bonded together with a covalent bond. This would be our example of intramolecular force. Whereas here, the connection that this HCl has for the HCl next to it, this is an intermolecular force, so the force between the molecules. All right, for our checkpoint, what must be added to a group of molecules in order to disrupt the intermolecular force? So if we go back to the example I was talking about before, we're talking about the force that would connect one water molecule to the one next to it. And if you think about it, how do we separate water molecules from each other? How do I get ice to turn into liquid water or liquid water to turn into steam? Or I'm separating these molecules out away from each other, and the answer is heat. So we use heat energy in order to separate our molecules and disrupt these intermolecular forces. So we turn up the heat. Adding energy in the form of heat will overpower the intermolecular forces, and they cause ice to turn to water and eventually to steam. And since this, of course, is a phase transition or a phase change, it would be considered a physical change. So throughout this entire process of ice to water to steam, the chemical formula is H2O the entire time. If I were to break intramolecular forces, that would mean actually breaking the connection between the oxygen and the hydrogen. So essentially what I would end up with is oxygen and hydrogen gas separated from each other. That would be an intramolecular force being broken, but that's not what we're talking about here. Here we're just saying this water is separated from the water next to it. All right, for our next checkpoint, we're going to look at two energy requirements for phase transitions. So here, even though this looks kind of like a chemical reaction, we have that arrow in the middle, one thing going to another. You can see that it's H2O the entire time. We're only changing the phase of matter. The S is solid, L is liquid, and G is gas. So I'm going from solid to liquid, and that requires 6 kilojoules per mole, and liquid to gas, which is 41 kilojoules per mole. Now, you do not have to actually remember these numbers, and the numbers themselves honestly aren't that important. The key thing that you need to see here, though, is that going from solid to liquid is less energy. Going from liquid to gas is a lot more energy. So for a checkpoint, why would it take more energy in order to go from a liquid to a gas? And the answer here is related to one of the pictures that we saw earlier, where we had each of the phases of matter within that Erlenmeyer flask next to each other. We noticed that the solids and the liquids were very similar to each other. The liquid molecules were maybe a little bit more spread out, but they were very close together still. Whereas the gas molecules, they were completely spread out from one another. So when I go from a solid to a liquid, I'm kind of straining the intermolecular forces a little bit, but I'm not completely breaking them. The molecules are still very close together and attracted to each other. Whereas when I go from a liquid to a gas, those H2Os are completely separating from each other. So since I need to completely break the intermolecular force, Of course, it's going to take a lot more energy in order to do that. So why does it take more energy to go from a liquid to a gas state? It's because the molecules in the gas state are completely separated from each other. So I have to completely break the intermolecular forces. So from liquid to gas, our intermolecular forces are completely broken. All right, that concludes part 6 of our Unit 2 notes. When we come back for part 7, our final part, we are going to be covering phase changes and the heating curve for water.